Hi, Mr. Who.
How's it going, Monty?
It's going good. What about you?
I'm doing great now. Thanks for asking. Um, um, okay, how's it going, everyone? To get started, we're going to take a look at this this particular question. Um, Actually, well, these particular vehicles. So these actually vehicles have all actually raced together in one drag race. So what I want you to do is I want you to answer which one of these five vehicles do you think would win in a drag race. You have an F-16 fighter jet, you have a Formula One car, a motorcycle, a Tesla Model S, and an Aston Martin Vantage. So which out of these five vehicles do you think would win in a drag race? Yes, it is a real fighter jet. And yes, they did race. There's also a private jet that was in here. There's also like another two other sports cars in here, but I only included these five because these five are the most interesting. So which one do you think would win a drag race? An F-16 fighter jet, a Formula One car, a motorcycle, a Tesla Model S, or an Aston Martin Vantage? So which of these would win in a drag race? F-16 fighter jet, a Formula One car, motorcycle, a Tesla Model S, and an Aston Martin Vantage. Um, the votes have been pretty balanced today. They're really, really, really unbalanced on yesterday. There's very strong consensus towards two of them. Today is more balanced. Um, 14 out of 15 people have already decided that they have an idea of which one would win. Oh, all 15 people voted. Okay. So normally I would have given you a couple more time, a couple more minutes, but since everyone voted, let's actually watch the video and see who would win in a drag race. So So if we go back and watch this last portion, this last picture right here, you can see that the motorcycle just edges out the Formula One car, and then they are followed shortly by the fighter jet. And then afterwards, you have the Tesla, and after that, you have the sports car. So pretty interesting. Most people did not pick the motorcycle. It seems that now it seems that most people picked the motorcycle. I wonder why. But originally, most people picked the Formula One car. Someone said that you thought the fighter jet would have beat them all. I think if it was long enough, I think the fighter jet would have beat them, but the race was fairly short. So since I know that most people did not pick the motorcycle, what I want you to do is I want you to try to come up with an explanation as to why did the motorcycle win the drag race. So how did a motorcycle beat an F-16 fighter jet, a Formula One car, a Tesla Model S, or an Aston Martin Vantage? How did the motorcycle beat all these cars? So I'm going to put you in your groups here, and I want you to try to see if you can come up with an explanation for why the motorcycle beat these particular cars. Yeah. Okay, okie dokie. So what we're going to do is we're going to take a look at why the motorcycle won. So one common theory that I heard a lot is something to do with the mass of a vehicle. So here's what we'll do. What I'm going to do is I'm actually going to sort of give you a ranking of all these vehicles here, and we're going to take a look at how the masses scale up. So what we're going to do is I'm going to call this the place, what place did the vehicle get? I'm going to call this the um, what was it? The vehicle itself. So in first place was the motorcycle. Second place was the Formula One car. Third place was the fighter jet. Fourth place was the Model S. Fifth place was the Aston Martin. And in last place, well, so I didn't include this in the poll, but I'm going to include it here just because I think it'll be interesting to see. So these are the 6 vehicles we're going to look at, and this is what place they got. So now let's take a look at the masses of these objects, and let's see if we can let's see if we can identify a relationship between these. So what I'm going to rank these also from the lightest to the heaviest. First being the lightest, and the 6th being the heaviest. So I think the motorcycle is the lightest. So I'm going to see the motorcycle as the lightest. I'm going to see the motorcycle's first place in mass. Formula One cars are notorious, not notorious, but they are very, very, very light for a reason. So I would say the Formula One car is definitely going to be the second lightest. Okay. So the fighter jets are going to be, and the jets, the planes are going to be definitely going to be heavier than the cars. So we're going to look at the cars next. The Model S versus Aston Martin. So Model S, this is an electric car, so this is pretty heavy. So the Aston Martin is definitely going to be lighter here. The Aston Martin is going to be lighter. The Model S is going to be fourth. The fighter jet versus the fighter jet versus the private jet. I think the fighter jet is going to be fifth, and this is sixth. Yeah. So honestly, if we look at this, the masses of the object, for the most part, actually correspond pretty well to the place they had, right? The lightest object had the best place. The second lightest object had the second best place. The fourth lightest object had the fourth best place. The heaviest object had the worst place. These two were flipped, right? They were flipped. But for the most part, there's a general trend where the lighter the object is, it seems like the faster it is. And that's an analysis that most of us sort of had some ideas about, right? We sort of assume that okay, the motorcycle is the lightest, so we think it's going to be fastest. And some other ideas I heard were because it's so light, there's not much gravity acting on it, which is true. Doesn't need as much force to get it to accelerate, which is also true. But the general idea is right. The lighter the object is, the faster it can accelerate. Yeah. So using this idea where the lighter the object is, the faster it can accelerate, we're going to use the same idea and we're going to look at gravity, how this affects the force of gravity in terms of our acceleration. So, but for now, before we get to that though, what I first want to do is first talk about why gravity is the way it is. So one thing I said last time was, okay, I want you to try to tell me why the force of gravity is the same on us as it is on Earth. And most of us were like, I have no idea why, because it's not very intuitive. So I'm going to tell you why. And this is something called Newton's third law. So this is a law in physics where it tells us that in every force, there is an equal and opposite force against it. So if I do something, there's going to be an equal and opposite force applied against me. So if an object A is pushing against object B with a certain force, object B is going to push back on A with the same amount of force, but just in the opposite direction. So when the Earth is pulling on me with its gravitational force, I am also pulling on the Earth with the same amount of gravitational force, just in the opposite direction. Basically, anytime something happens, anytime there's a force, there's going to be a force in the opposite direction that is going to be equal in terms of its strength and equal in terms of its force, but just in the opposite direction. So that's sort of how gravity works. Every time one object pulls on another, that other object is also going to pull on it. It's an opposite. It's a what we call equal and opposite force. We also can call this action reaction. So when there's an action, there's also a reaction. and these action reactions are also equal. So what I want you to do is that I want you to, in your group, I want you to try to come up with 3 examples of equal and opposite forces, which we sometimes also call action reaction forces. So gravity, for example, is one example of an action reaction force, but there are lots of action reaction forces in the world. And I want you to see if you can come up with at least 3 of them. So I want to put you in your groups again. And when I put you in your groups, I want you to try to come up with 3 examples of an action reaction force. So what we're gonna do now is I want to give you guys a chance to, I'm gonna give you guys a minute or so, and I want you to type in an action reaction force. You don't have to enter yet. I'm gonna give you a minute or so. I want you to type in an action reaction force that you or your group came up with. You can put in as many as you want. It's up to you. But I want to try to get as many action reaction forces as we can. We'll take about a minute or so, and then in a minute I'll tell you to hit enter, and then let's see what action reaction forces we are able to come up with. I heard a lot of really good ones, so I want to see some really cool action reaction forces. They are very present in your life, very present. You literally can't do anything without an action reaction force. Everything has to be done. Yeah, you can't even. Yeah, everything has to be. It has to action. There's action reaction forces everywhere. So about another 30 seconds or so. Type in the chat an action reaction force, maybe more, that you and your group came up with. And then in about 15 seconds or so, I'm going to tell you to hit enter. And then let's see what ones we can get. All right, 5, 4, 3, 2, 1. All right, hit enter. Hit enter. Let's see what action reaction force we're able to come up with. Let's get the chat going. Let's get the chat popping. So I'm gonna start reading through some of these. We had some really good ones. As I'm reading through these, please keep sharing your ideas for action reaction forces. One of them is jumping. Yes, jumping is honestly a really good example of an action reaction force because it's physically impossible to jump without an action reaction force. So if you think about it, if you imagine what's happening when you're jumping, you are physically pushing off of the ground, right? Like that, and the more you push off the ground, the higher you can jump, right? So if you just try to like jump without really like bending your knees and stuff, you're not really pushing on the ground a lot, which means you can't really jump up very high. The more you sort of crouch and the more you sort of springy you get, the more you can jump up. So you can't jump up if you're not pushing off the ground. And that's because when you push on the ground is also going to push up on you and push you up into the air once you sort of release. So yeah, jumping is a great example. Playing baseball when the ball and bat make contact. Yes, this is a great example. So right when you're playing baseball, you hit the ball with your baseball with your bat. The bat is going to contact with the ball. The action is going to cause the ball to go forward. However, the ball is also going to hit the bat. So that while the action is the bat hitting the ball, the reaction is the ball hitting the bat. And when the ball hits the bat, if it hits the bat hard enough, it can actually cause the bat to break. So, and the bat breaks because of the reaction from the ball hitting the bat. So that's a great example of an action reaction force. Swimming is a really good example of an action reaction force. And this sort of relates to the next one, pushing off against a wall. So if you're swimming and you sort of like, and you're by the wall and you push off, right? When you push off of the wall, it's sort of similar to jumping. You are applying a force into the wall, and the wall is going to apply a force into you and sort of push you forward. Also similarly, when you're swimming, right? If you like push against the water is also going to sort of push you forward. Also a really good example. When one pool ball hits another, that's also a good example, because when the pool balls come into contact with each other, the pool ball that's being hit will sort of apply a force to the pool ball that's hitting it and sort of slow it down. So that's a good example of one as well. Kicking a ball is really good. Kicking a ball is really good because if you kick a ball really hard, the ball is also going to hit your foot as well, which means your foot can hurt. So if you're kicking a ball really hard, the ball will apply a larger force to your foot, and it can actually, do some damage to your foot if you kick it hard enough. So yeah, I think a good one. A person diving off of a raft. So this one's really cool because like this sort of works if you're on like ice or if you're like in a chair or something. So if you're in a raft and you're pushing off of the raft, as you go forward, the raft is sort of going to go backwards. And that's because you are literally, the raft is pushing you forward and you are pushing the raft backwards. And there's sort of a reaction as you're going forward, the raft is going to go backwards. So that's also a really cool action reaction force. At baseball, when the bat hits the ball, this also is a great one example. Yeah, so these are also really good examples of action reaction forces. So thank you for sharing. So the reason why we talk about action reaction forces is because that's literally how the force of gravity works. You have an action, you have a gravity is one action, and then the force of gravity from the other object is the reaction. So the Earth pulling you is the action, and the reaction would be you pulling the Earth. and those forces are going to be equal and opposite in magnitude. The key word is equal. They are equal. The force of gravity acting on you is going to equal the amount of force of gravity at Earth that you are putting on the gravity. But this is really weird because the Earth doesn't really move. If I jump up on the Earth, I'm going to fall to the Earth. The Earth is not going to fall towards me. So why is this the case? Because you said, Mr. Hu, that the forces are equal. So how can they be equal if the Earth is not moving? If I'm the one moving, but the Earth is not moving, which hardly seems equal and opposite. So, and this is where we're going to talk about something called, we're going to use the equation force is equal to mass times acceleration. So the amount of force acting on an object is going to equal its mass times acceleration. This is a very important equation to know, so I would definitely write it down somewhere. The amount of force acting on an object is going to equal its mass times acceleration. So what this means is if I'm applying a force on an object, if it has very low mass, it's going to have a very high acceleration. If it has a very high mass, it's going to have a very low acceleration. And this relates to the warm-up, right? With the warm-up, we noticed that the motorcycle had the least amount of mass, which helped it attain the highest acceleration. And as the mass of the objects kept increasing, what we noticed is the acceleration kept decreasing. So there's a relationship between the mass and the acceleration. And the general relationship is that the higher the mass, the lower the acceleration. The lower the mass, the higher the acceleration. So, which is why, when you're dealing with any sort of high performance vehicle, you want to make it as light as possible so you can help it accelerate as fast as you can. And so the amount of force acting on an object is going to equal its mass times its acceleration. And so the lighter an object is, the more acceleration it has. The heavier an object is, the less acceleration it has. And so we're going to try to use this equation, and we're going to use this in the equal and opposite forces, and we're going to try to look at how much you accelerate when you're under the Earth's gravity, and how much the Earth accelerates when it's under your gravity. So what we're going to do here is we're going to calculate the acceleration due to gravity. So using the force of gravity we calculated last time, which if I remember correctly was 734. So this is 734 is the amount of force that the Earth exerts on you. So what would the acceleration due to gravity be that the Earth experiences, and how much of this acceleration due to gravity that you experience? You're going to use the force of gravity that we calculated, 734, and we're going to use the equation force is equal to mass times acceleration, and we're going to calculate how much acceleration you experience and how much acceleration the Earth experiences. So we're going to use this equation, we're going to use the force here, and we're going to calculate the accelerations due to gravity that you experience and the Earth experiences. And then I want you to try to see if you can try to make sense of these accelerations. See if you can try to find some reasoning behind them. So once you have the amount of force, either hopefully you wrote it down from last time, but if you haven't, it's set right here, 734. So once you write that down, once you have your equation ready to go, I'm going to put you in your groups, and I want you guys to try to come up with, find the acceleration due to gravity that the Earth experiences. what I'm going to do here is I'm going to quickly go over sort of how you can calculate the gravitational force and gravitational acceleration, and let's go over what it means as well. So in terms of how can you calculate the gravitational acceleration, what we're going to do is we're going to use the equation F equals ma, because that's the equation we can use to calculate the acceleration if we're know the force. So assuming that using the equation F equals ma, the F equals the force that we experience, and this F is the force, and that's the mass, A is the acceleration. And so we know that we and Earth both experience a force of 734 units. So let's try to figure out our acceleration. So to figure out our acceleration, we're going to use this equation here. Now the question is, how much force are we experiencing? So as we found out earlier, as I wrote down earlier, what we calculated last time was that we and the Earth both experience a force of 734 newtons. So that would be our force. And this is going to equal our mass times our acceleration. Now our mass in the problem is 75 kilograms. And we're trying to find the acceleration. So now that I've set it up, to solve for this, I just divide both sides by 75. So what I get is that my acceleration is 9.8 meters per second squared. Now, one of the things I've done in the past previously is I said, let's try to find the gravitational potential energy. And so you probably did something like PE is equal to mgh. And I said G is 10. Well, here's the thing, right? G is actually a measurement of the gravitational acceleration. And what we just found was the gravitational acceleration. So actually, this number is actually really G. G here was, now we rounded it up to 10 to make our life easier, but the actual number here is actually 9.8. And that's actually where it comes from. This 9.8 is actually a measurement of how much we accelerate due to the Earth's gravity. And so this is actually where it comes from. So last time I just said, hey, this is G is 10. This time we actually know that we can actually calculate it, and it's actually 9.8. So this is where it comes from. So what this means is that every second we are, if we're falling, every second our velocity speeds up by 9.8 meters per second. So we're basically moving pretty fast here. Now let's talk about Earth's acceleration. So we're just going to use this equation, F equals ma. So the question is, so we know how much force we experience from the Earth, 734. So how much force should the Earth experience from us? Well, once again, we're going to use this concept of equal and opposite forces, action, reaction. So if the Earth is pulling on us with a force of 734 newtons, we are also pulling on the Earth with a force of 734. So once again, the force is going to be 734, the same as the last time. However, the big difference this time, though, is that the Earth's mass, instead of being 75, is 5.97 times 10 to the 24 kilograms. This is a very big number. So when we divide this out, on both sides by 5.97 times 10 to the 24, what we get is that our acceleration is something like 1.2 times 10 to the negative 22. Now, if you aren't really sure what a negative exponent is or what the significance of this means, so when something is 10 to the negative 2.2, what this means is that there are 22 zeros. So there's 22 of these zeros before we get 1, 2. So there's 22 zeros before 1, 2. So this number is tiny, absolutely tiny. So the Earth is technically accelerating, but it's accelerating at such a small number, it's basically zero. It's like it is accelerating. We think that the Earth is technically accelerating, but compared to how much we're accelerating, the Earth is basically not moving. So this is why, even though we and the Earth can both experience the same gravitational force, this is why that we move and the Earth doesn't move, apparently, because we are so much less massive than the Earth. So even though the thing is that how much you move, it turns a lot based on how much your gravitational force is, but also your mass. So when two objects are experiencing the same force but have different masses, the lighter object is going to accelerate more, and the heavier object is going to accelerate less. So that's sort of why, even though we and the Earth can experience the same gravitational force, why the Earth doesn't move, and why we move so much. Okay, so it's 1:09 now, so we're just gonna time to wrap up now. No homework. We're just gonna continue this on Friday to continue talking about elliptical orbits and stuff. So that'll be it for today, and I'll see you guys on Friday.
Thank you, Mr. Hu.
Thank you.
Thank you, Mr.
Thank you.